So with solving by factoring, right, or just solving in general with these types of problems, it's, we're finding solution. It doesn't have to write in black. Finding solutions, which we talked about the other day, being the same things as zeros, which is the same things as x-intercepts, which is the same things as roots. Okay, so if we want to find solutions, then we need to have one side of the equation be equal to 0. Right? We're trying to find those zeros where what x values make y equal to 0. So when we look at a problem like this first one, just realizing that it's not ready yet to solve because it's, one side is not 0. So that's where kind of we need to start with this. Now let's get one side to be 0. So I'm going to go ahead and subtract 6 over. I did see a couple people making kind of silly mistakes in that regard. They're just making the side 0. It's like, boop, 6 is gone. It's just 0. Right? It's not about just turning it into a 0. It's about getting that side clear of any terms. So make sure you bring them over to the other side. And then once we have everything gathered, we say, oh, why don't we just get x by itself, right? Well, we can't get x by itself because there are multiple types of x's, and so there's no way for us to isolate x if there's no way for us to get it down to just one x. And so we had to have another tool, or if that didn't, that became the factoring. Like, how do we break this thing down to see where it came from and get those x's to be isolatable? And so that's where factoring came in. And what type of factoring are we always supposed to try first? GCF, right? And so, do we have a GCF here? No, right? So nothing in common, so we need to move on to the next thing, right? So we talked about, if there's 4 terms, we should try grouping. If there's 3 terms, then we should try AC methods. We definitely see, 3 terms here, and so we need to take our A value times our C value, and that gives me 4 times -6, which is -24. And then we need that -24 to add to be 5. So what are our factors of -24 that add to be 5? Yeah, almost Sam, but yeah, should be 8 and -3. And Tion, if you see the comment I made on your paper, this is what I was referring to in regards to like finding your AC that adds to B, where you were struggling. So we take that 4x squared, and then we need to, we said positive 8, so it's positive 8x, and -3, so it's -3x, and then the -6 comes down. And do make sure you're not dropping off that equals 0. It does need to be there as part of your work. It still needs to stay an equation. I definitely notice I start writing smaller and smaller as I move down my paper. So then we break that in half. So now we can factor it by grouping since there's 4 terms, and noticing that the 4x squared and the 8x both have 4x in them. And that means I'm 4x times x, and then 4x times 2. And then -3x and -6 both have a -3 in them, which leaves me an x and a positive 2 also. And I don't force it to be x plus 2. I'm checking to see if it is x plus 2. I want them to both be x plus 2 there. And since they are both x plus 2, I can factor that out. X plus 2, and then we lift our leftovers here, the 4x and the -3. Still equal to 0. So this is that part where we got to say, well, now I can isolate x, because if one number times another number is 0, then one of those numbers must be 0, right? So this must be 0, or this must be 0. And so we stopped and said, well, what x value would make this 0? So we'd say x plus 2 equals 0, and then we would just subtract 2 over, and so x would be -2. Well, what about the other one? What x value would make that 0? 4x minus 3 equals 0. So we would add 3 over. Then we would divide by 4. Oops. And so we get x equals 3/4. I do want you guys to leave your answers as fractions, not turn them into decimals. Okay? So there we found our 2 solutions. We found our 2 zeros, we found our 2 roots, we found our 2 x-intercepts. So if we go back to the equation, kind of think about, again, what this really relates back to. So looking at this equation here where I had everything on one side of the equal sign, and think about what that would look like. Oops. so, looking at the equation, we know that the y-intercept is -6. Then we just saw that one of the x-intercepts is at -2. The other one is at 3/4, which just be that shy there. And so this graph must look something like this. It is a parabola since it's a square. So we'd have -2, 0 there, and then 3/4, 0 there would be our x-intercepts, and then 0, -6 would be our y-intercept. So just kind of getting an idea of how those things kind of all play together with our solutions, like how they actually go back and relate to the graph of the function. Okay? So we talked about solving by factoring already. But here's another one we want to try.
I have a question.
What's up?
Okay. So the -6, did that just come from the problem, or?
Yeah, that was right there.
Well, yeah, but.
Oops.
So. Okay, never mind. I actually get it now. I was just confused for a second.
No worries. Yep, that was just, remember that C value is our y-intercept when we put it in standard form.
Okay.
Anything else on that first one? We'll go into the second one. Okay. So looking at the second equation, right, we're solving this by factoring. What method should we use to factor this? We could use AC, Sam, but I don't want to. There's a better way.
Is it square root?
You probably are trying to say the right thing, but yeah, you're saying it wrong. It does deal with squares. That was part of it. There you go, Kyla. Yeah, the difference of two squares, or difference of squares, usually what I say. So two terms, we saw Monday or maybe Tuesday, how to factor the problems that have two terms. So it was the difference of squares or the sums of differences of cubes that we can do it faster. And Aiden, I'm going to ask you to back up just a little bit. So Aiden, when we do factor difference of two squares, what do the answers always look like? What's similar about all of the answers whenever we do factoring by difference of two squares? Yeah, so I'm probably saying a little bit too much there, and it's not always just x plus and x minus, but it is, those two things, and we got the plus and the minus, right? We don't necessarily know what's going to go in the front or what's going to go in the back, but it's always the two sets of parentheses, and one has a plus in it, one has a minus, and other than that, they're exactly the same, right? They're kind of mirrors of each other, and then we say, well, what gives me x squared? And that's x times x, and then what gives me 25, and that's 5 times 5. Again, Sam, we could have done the AC method on there, but by recognizing it as a difference of two squares problems, we're able to do it a lot faster, right? So just see the lack of steps we had to go through, right? It's that pattern-based factoring that if the problem looks like this, the answers will always look like this other thing, and we can just basically jump straight to them. Does that make sense, Sam? So we want two terms, subtraction, and they both have to be perfect squares. Then we can use this kind of shortcut on the AC method, right? And so then we're ready to solve, right? We got x plus 5 equals 0. So subtracting 5 over, that means that x will be equal to -5, and then x minus 5 equals 0. So adding the x 5 over gives us x equals 5, right? So there's our solutions, there's our roots, there's our zeros, there's our x-intercepts, right? So again, just kind of going back to think about what that would look like as far as the graph. Just kind of sketching out, just kind of getting an idea of things. We have one x-intercept over here at -5, got another one over here at positive 5, and then we've got our y-intercept up here, right, way down there at negative 25. So our graph is, going to be going through that, and the vertex would actually be there in the middle, right? If we think about the intercept form, that told us that the axis of symmetry had to be in the middle of those two things, and that would be the 0 would be the middle of those two numbers. So our graph would look something like that. So again, just what do these things actually mean, like in relation to something else, right? They represent those 2 points on the graph. Okay. So we've talked about this method of solving, and again the reason we had to have a different method is because there was multiple types of x's within the problem, right? That's why we had to go and do this differently. But wait, there was only one x in this problem. So could we have done this in a different way? Because I had to factor this because I had these multiple types of x's, but here there's only one type of x. Literally there is only one x in this problem, okay? So could we have done it a different way? Yeah, we could have actually. And so that's what this next method is going to be about. How do we deal with it when there's only one type of x? Could we do this in a faster way? Or in sometimes when they're not factorable? This problem that we're going to do first, obviously, is the same problem, the one there on the left. I want to show you a different way of doing it. But pretty much everything else from here on out won't be factorable, in a way that would be useful. So how do we approach it from then, right? So here's our next method of solving. It's going to be solving by using square roots, okay? And so somebody in third hour asked a really good question about, like, how do we know when to do what, right? Well, right now we're just going to be focusing on this method, and your homework tonight's going to be focusing on this method. But come test time, late next week, probably next Friday, it might very well say on your test, like, solve by factoring, solve by square roots, solve by mystery method we're going to learn on Monday, okay? And so we'd be testing that particular skill, so we want to see if you can do that or not. But there may also be a problem that just says solve, and you get to do that however you like. And so sometimes there is a choice, and sometimes it's really a choice that's kind of made for you by what the problem looks like. And certain problems are only going to be solvable with certain methods. So just understanding, like, when can I do what? When should I do what? Okay. So really, this method of solving by using square roots really is more akin to what you guys are used to solving, like thinking about solving. When we solve linear equations, it's all about just getting the variable by itself. Since there's only one x in this problem, I should just work on getting it by itself. That's how I should solve that. And since we're doing that, we need to think about SADMAP. What do I undo first? What do I undo next, right, in order to get x by itself? Okay? So just notice how structurally different this problem is than the first problem. The first one had two types of x's, x squareds and normal x's. So there's no way for us to isolate it down to one x. Here we just have x squareds, so we should be able to get it by itself. So I want to look for any subtraction addition that I need to undo first. And here, of course, we have a minus 25. So the first thing we do is add 25 to both sides. That's going to give me x squared equals 25. Right, so that level of that is done. Looking for any division multiplication to do. There's nothing over here to divide or multiply by, so don't need to worry about that step. Then we look at exponents, right? Well, there's an exponent. What's the inverse of squaring, right? How do we undo a square? Right? We do that with a square root. Right? And so if I want to square root both sides to get rid of that square, so on that left side, the radical and the exponent just cancel each other. And so we're down to x. Now here we need to be really careful, because here's where a lot of students start making a mistake. Okay, there's a difference between this and this. Okay. If you're ever asked, like, what's the square root of 36, or if on a test or homework or something like that, it just says square root of 36, like it's printed there. There's one answer to that. The square root of 36 is 6. Okay. If you're asked, what number squared is 36, which is what this says, what number squared is 36, there are two answers to that question. Right? The fundamental theorem of algebra says that the exponent tells you how many answers there are to the question. So there are two answers to this question. Just like we know there are two answers to this problem. We just found them. Right? We just found two answers. We know there are two answers. Right? So when you square root, right, the square root wasn't here in the problem. When you square root both sides, you have to address the fact that there are two answers to that problem. One of them is positive and one of them is negative. Because there are two numbers that I can multiply by themselves to get 25. Right? I know this is something we've talked about before as far as this plus minus business, what that means. Okay, it just means x equals positive 5 or x equals negative 5. It's just shorthand. And if you're not really comfortable with that shorthand, you don't have to write it that way. You could also write x equals 5 and negative 5. Don't put parentheses around it because it's not a point, it's just a list of numbers. Or you could write it out twice. But quite literally, it is just the shortest amount of writing, so it's shorthand, right? But they all mean the same thing. Okay, so when we square root both sides, we must deal with that positive and negative aspect to the solution to that. Okay, so this is by far one of the most common mistakes people make when solving by square roots is they forget that they have to have a positive answer and a negative answer to their question. Okay. Does that make sense?
Yeah.
So every one of our problems today should have two answers. Okay. Let's look at a different one. Right? We know we could have solved that one by factoring. Okay. But, could we do that here? One thing just about solving, right? That when you have x's on both sides, we want them together. Okay. So looking at a problem like this and saying, okay, I've got x's on both sides, let's gather them first before I try to do anything else, right? That's a pretty normal step as far as solving it. Really, again, most of this stuff should be just like solving equations back in Algebra 1. It's just a little bit more complex, but the general method's really the same. So I want to think about, SADMAP again after I gather things. Let me gather things first, I guess. So adding 3x squared, you should always move it towards the larger of the two, and of course 2 is larger than negative 3. So that'd give me 5x squared minus 30 equals 0. Right? So we knew the last one was solvable by factoring as well. Could we factor this one in order to solve it? So looking at that left side, you say, well, can I do anything with this, right? I have a GCF, right? So you guys don't need to write this down, but we could take a 5 out of both, and then it'd be x squared minus 6 equals 0. And so then looking inside the parentheses and saying, hey, can I do more of that? Oh, there's two terms, there's a subtraction, and they're both perfect squares. Oh, wait, they're not both perfect squares because 6 is not a perfect square. So the difference of squares method of factoring doesn't work on that. Like, well, I could always try AC method, though. That worked before. And so my A value would be 1. My C value would be negative 6, so A times C being negative 6. And then my B value would be 0. Are there any factors of 6 that I could manipulate to get 0? Well, 1 times 6, can't get 0 out of that. 2 times 3, can't get 0 out of that. So this problem is not factorable anymore in a way that's useful. I can't break the x's apart. So factoring stops working on a problem like this. So we got to have a different way. Okay? Doesn't mean there aren't answers, it's just that tool doesn't work. Okay? So starting to see that factoring doesn't work all the time. So what do I do, right? So we bust out SADMAP. So I want to get rid of any subtraction addition first. So of course, I'm going to add that 30 over. So 5x squared equals 30. There goes our subtraction addition. And then we got any division multiplication we can get rid of. Of course, we can get rid of that 5. So it gives me x squared equals 6. So division multiplication is done. And then get rid of a square by square rooting. So again, on the left side, the square root and the square just cancel, so they're gone. And we're down to positive and negative square root of 6. So don't forget about that. And that's when it should show up, right? Right after we square rooted, that's when that needs to show up. Okay. Now, the last thing we need to do, like kind of like with a lot of problems, is the last thing we need to do is just check to see if our answer can be reduced. Okay. And so we want to look at this and say, can we reduce that? And this is where that skill that we worked on yesterday comes into play. Can we reduce, or can we simplify this? Here's the problem we're working on, Caitlin. So what's our method for reducing this, right? We want to take that 6, we want to break it apart, right? Use our sock on that and say, what can I break 6 down into? Well, that's 2 times 3. And that's it, right? There's no more factoring to do there. So once we had it all socked out, what did we look for? Yeah, buddies, right, Audrey? Right, and Audrey, do we have any buddies here? Nope. Right, and so, but only if you had a buddy could you come outside, right? And nobody has a buddy here, so the 2 and the 3 just need to go back in. And when they go back in together, they, of course, they just multiply back together. And so that is as far as our answer can go. X equals plus or minus the square root of 6. So it gets a little bit harder to visualize though, right? The square root of 6 doesn't really mean that much to us. Whereas like when we got 5 and negative 5, we kind of understood what it was going to look like. So, but what is talk about it just a little bit. I'm going to go back to this version of the equation where everything was on one side. Okay, and just talk about the graph of that real quick. Okay. So if I think about that, if it said y equals this, then I could just graph that real quick. So if we think about what the square root of 6 would be equal to, well, the square root of 4 is 2. The square root of 9 is 3, right? So the square root of 6 has to be somewhere between 2 and 3. Okay, wherever it is, it's somewhere between 2 and 3. And it'd be positive 2 and, or, you know, on the positive side and the negative side. So somewhere in there is that point. I'm just going to put it about in the middle. Okay, we're just talking right now. Then we also have our y-intercept up here, this negative 30. So way down there at negative 30, I have my y-intercept, so this would be at 0, negative 30. This point would be at square root of 6, 0. This one would be at negative square root of 6, 0. And then our graph would do something like this. So even though the numbers stop meaning as much to us, right, square root of 6, right, we can still understand that it's just a place on the graph where the graph is crossing the x-axis. Okay. Anything there with kind of our introductory problems you guys want to talk about before we move on to the next one? I'm going to do one more with you, and then I'll have you guys try one on your own. Yeah, sure will, Audrey. Do you need me to zoom in or anything? Okay. So, I mean, if there's anything you guys need me to kind of like highlight a little bit more as we're doing this next one, or this really is the process. We're just solving. Okay, we're trying to get x by itself or whatever letter by itself each time, or so we just be hitting SADMEP each time. Just kind of working with the radicals as we, just trying to work on that skill that we picked up yesterday as it relates to these problems. Right? So the problems are just going to get a little bit messier each time. But the general idea won't change. All right. So I'm going to do the one over here on the left with you guys, and I'll ask you guys to do the one on the right. Same method. Nice hat. Okay, so we got a fraction there, 1/2 y squared plus 15 equals negative 25. So just gonna write our buddy SADMAP over here. Just keep ourselves focused, right? Get y by itself. Let's undo things in the right order. Okay. So, Tion, what should we do first? Subtract 25. And we want to get y by itself. So we want to get things away from the y. So you should be more focused on this side of the equation. This stuff's already away from the y. I want to look over here and say, what can I get rid of? So what do you think, Mason? What could we do? Tion needs a little help. Oh, he's fast. Yeah, I want to subtract the 15. It's almost like he knew I was about to ask him. Does that make sense, Tion? Want to move stuff away from the y to the other side? And then negative 25 and negative 15 would give us negative 40. Where should we go next? All right, so our subtraction, addition's done. Where should we go next with this? Division, multiplication, we can get rid of. So we're going to divide by, Audrey. Make sure you're being specific. I don't generally like to divide by fractions. People don't understand division by fractions very well. It's a pretty good chance that if I ask you what's 10 divided by 1/2, you're going to tell me the wrong answer. So 95% of people will tell me the wrong answer if I ask them that. So dividing by fractions is not a great thing for us to think about. What should we do instead? All right, so Kyle's saying multiply by the 2, right? The 2 is dividing, right? That's what makes it a fraction. It's dividing, so let's multiply it out of there, right? And so, of course, on that left side, the 2's cancel, and that would leave us with a 1y squared. Well, we don't need a 1. Right? 1's not doing anything for us. If that had been like a 3 or a 5 or something like that, we would need to deal with it. But since it's just a 1, we don't need to worry about it. So we just got y squared over there. And of course, 2 times 40 being 80, so negative 80. So there's our division multiplication step. Can't you convert the fraction, though? What do you mean by that, Audrey? What do you mean convert the fraction? Did you mean like to a decimal or something? Or are you trying to say something about like, yeah, I'm still like, makes it easier to type into a calculator, but still like mentally, like if I say, hey, what's 10 divided by 0.5, still it gets kind of tricky for people to understand. Whereas if I say, what's 40 times 2, that's much easier for us to understand. 40 times 2 is 80, of course, and 40 divided by 1/2 is also 80. Which of those is easier to understand, right? And so that's where I'm kind of going with this, is that we just don't think about dividing by fractions very well. Most people don't think about that, right? And so let's do it with a way that makes more sense generally. But yes, mathematically it works. It's just most of the time we don't think very well that way. So that's all I'm trying to avoid. All right, so let's get rid of that square, right? That's our next step. Square root. Of course, again on that, left side's just canceling. And then we have plus minus, right? Because we just square rooted. Don't forget your plus minus. It's really easy to do. Square root of negative 80. And so just like last time, we just, we're really done, right? Y is by itself, but it's just about getting it down to something more simple, something more reduced, right? So we're done solving. It's just about simplifying this right side now. Okay? And so what does this tell us about our answer? What does this right here tell us about our answer?
I think you have to use the.
Oh, sorry.
You have to use the I.
The I. Okay. What were you gonna say, Audrey?
I just said that. Yeah.
Okay.
The I.
Yeah. So I. Why do we use the letter I though? What does it represent? Why the letter I? Why not like an M or a P or a V or something? Why I?
Imaginary numbers.
Imaginary numbers, right, Andre? So I is our imaginary number, and so that's something we defined yesterday. That when we go to square root -1 in particular, right? That's equal to I, right? This is what I is equal to, and I talked to you guys yesterday. You really need to know that. It's almost like vocabulary. You need to know this value of this letter. Okay, it's what it's defined as. That's its definition. So it's essentially like vocabulary. Okay, so when we go to square root negatives, we have to have an I in our answer. Just how it is. Okay? And so we talked about let's break that apart. Let's talk about the positive part of that square root times the negative part of that square root. So then we can focus on the 80 separately from the -1, right? Just take the -1 away. We'll deal with it later. Let's worry about the 80, right? And so this is where we need to sock out that 80. And so we 2 times 40 and 2 times 20, 2 times 10, then 2 times 5. And like that, you guys kind of or some of you guys have a different way of thinking about this, right? So we go and find those buddies. It's kind of fun to think about that. We find the buddies and then find the lonely 5 there, right? And so as we go to think about our answer, so y equals, and we definitely don't forget about our plus minus, so we make sure we bring that down. And then remember, each of those buddies gets to come out as one group of 2's, right? So this is a 4, the square root of 4 being a 1, 2, right? So 1, 2 gets to come out here. And then this other group of 2's also gives us another 2. And what do those 2's do to each other when they both come out? Yeah, right, Kyle, they multiply it. So 2 times 2 there being our 4. And then we have our square root. And then we have our 5 that was lonely, so he's staying inside. And then I talked to you yesterday about how that I, right, square root of -1 is I. How we do not put it here after, right? Because we don't want it to look like maybe it's underneath the radical or not. We don't want to leave that kind of in that ambiguous like, where is it? We never put it there. We always put it in front of the radical, but after the normal number. Yeah. So here's our final answer. That's as simple as we could make it. As crazy gross as that number is, it's the simplified answer. I'm sorry. Oh yeah, no, I wanted to write that there because imaginary, right? There is no real square root of -80, so we had to come up with this other set of numbers that were imaginary numbers that deal with the square roots of negatives. Those were our imaginary numbers. So again, I want to kind of go back to the graph on this because you look at something like 4i square root of 5 and you're like, what the heck is that thing? I don't know what that's just this blob of numbers and symbols and letters and stuff. Like, it's really hard to like conceptualize what that actually is because it's imaginary, right? Even like the square root of 6 is hard to think about, and this is messier than that. So I want to just talk about like what's going on here. Go back to the graph again. How do we see this on the graph? I'm going to do a little imagination game here with you. So I'm going to come back up to this part here. going to change this to an x just so it's more normal for us instead of being a y. Okay. I'm also going to push the 40 over to the left side so that it's plus 40 instead. So I'm looking at this equation. Okay. So as I draw this, that's what I'm drawing. So just making it an x so it's more normal for us, and then getting everything onto one side, which is how we would normally graph it in standard form. So what that would look like. Right, so think about what we know about this graph just by looking at the function. It's a parabola. It opens up because this is positive, and then its y-intercept is at 40. So up here at 40, we have this open up parabola thing, and if we thought about it, it might be a little bit wider than normal for a parabola because it is being compressed, right? And we squish it down this way, it goes wide that way. So our graph would look like that. And so we keep talking about, these solutions should be our x-intercepts. Well, this graph doesn't cross the x-axis. It doesn't have x-intercepts. So then when we think about this idea that it's imaginary, right, there are no x-intercepts. The only ones we have are imaginary. They're fake, right? They're not really there. So how that connects, right? These imaginary solutions don't appear here, where we would normally see our real solutions. Like, even as messy as it is, the square root of 6 is still a real number. And we saw 5 and negative 5. Those are real numbers. So we saw where the graph hit the x-axis. Well, these imaginary numbers don't show up here. Okay? So the equation still has solutions. We just had to come up with this new set of numbers, but they don't relate to our real graphs. Which of course begs the question, like, why do we need imaginary numbers? Very, very high likelihood that you guys will never work with an imaginary number in your life. Okay. Where the big applications are, right? We talk about applications of quadratics, we talk about motion and your glasses lenses, your contact lenses, satellite dishes, like all that stuff. Parabolas deal with, parabolic stuff deals with those types of things. Bridge supports and stuff like that. Structural elements. Imaginary numbers. One of the main applications of imaginary numbers is in electronics. So if any of you guys are at all interested in like building electronics, designing like computers and stuff like that, imaginary numbers will be important to you. Okay, if that's not something you want to do, a really good chance you'll never work with imaginary number again. Okay, but they do have applications. Again, my main understanding of imaginary numbers is that when you pass a current through a wire, okay, so if there's a wire running here and there's current running through it, that current creates an electric field around, or a magnetic field around the wire. And the mathematics that goes into how the current flows and then how the magnetic field is created deals with imaginary numbers. So again, if that's where something that interests you lies, then you definitely need to know this math. But if you think about how important that is to our daily lives, that we understand current and magnetic fields, it's super important. Everything that we look at, we're looking at right now with this computer stuff, all the technology we depend on is based around electricity and circuits and stuff like that. It's so important for the design of that stuff that somebody understood imaginary numbers. Okay. Again, it may not be, if all you're interested in is that when you hit your button on your phone that it turns on and does what you want it to, then you're done, right? But if you're interested in the design of those things at all, working with those things at all, then the math there becomes really important. So, okay. I want you guys to try this one. Send me what you got in the chat. So I'll stay over here so you guys can see that. Close, Sophia. Missing a little bit of something that's messing with you, keeping you from just a little bit further than you need to. So missing a sign. I want to check on that. Once you have that sign, you should be able to take your work a little bit further. Or if you want to type the square root sign, you can always use the Option V on your keyboard. Doing that with the Mac. So I've seen people type in the plus minus today. Pretty acceptable. This is a little bit harder to see sometimes. Somebody else earlier today just type it out as a list. Like that. What you think, Caleb? What you think, Aiden? Yeah, there you go, Sophia. What you think, Sam? What you think, Zoe? Yeah, that's good, Caleb. You actually have a little bit too much stuff there. If you think about maybe the simplest way to write that, you could write that with less stuff. That's right. No, you took out the wrong stuff. All right, here's what you guys should be getting. Just plus or minus I. So remember the definition of the square root of -1 is just I. We don't need to pull that apart. We don't need to have the square root of 1 times the square root of -1. There's no need to do that because as soon as you see this, this is already defined, right, as just being I. You just go straight from there to there. Just like if that said the square root of 25, I wouldn't need to sock that out or anything like that. I just know the square root of 25 is 5. I'm done. Okay. What do you mean by that? Focusing on the negative too much, Aiden? Do you need help, Aiden, or you think you got it? Yeah, really. I mean, confusing yourself with the negative and the square root is just, it's kind of silly. You are overthinking it because the negative and square root just means there's an I in my answer. Like that's really the easiest part. When I look at the square root of -80, the negative is just an I. Boom, I know that. It's the 80 that I don't know what the 80. That's the 80 I don't know. What's 80 made up of? How many 2's am I going to find in there? And then the grouping and the buddies and the lonely guy. That's where all the work is. The negative is just the I. So if you can just simplify it that much, like as soon as I see a negative inside, I've got an I in my answer. Just kind of keep that, sitting over there in the side of your head, and then worry about the 80, which is really where all the work is. So yeah, that's part of the reason too, Kyle. Is I wanted to do this problem because it is so easy. A lot of times students get freaked out, like there's got to be more. I'm doing something wrong. Like what do I do because it's so easy? Well, there it is. So yeah, sometimes the easy problems are the ones that wig people out. Can't tell you how many times I've gone through like a bunch of factoring and then I give somebody a GCF factoring problem. They're like, I don't know what to do. I'm like, we do GCF all the time. Like it's part of every other type of factoring. And they're like, oh, I'm gonna get all freaked out by an easy problem. So yeah, there it is. Not an uncommon thing to get weirded out by easy problems. So. I wanted to definitely show you, we're kind of running out of time here. I definitely want to show you one more problem. If we have time, we can try to do the other one too. Let's see. But again, just following through on SADMEP. This one's going to look the most like what we're going to do on Monday. So definitely want to just kind of show you guys what it looks like. And so, just following through on SADMEP and think about really, making sure that you're thinking about those parentheses, right? The parentheses is the very last thing I get to deal with. So that y plus 3 is kind of like in this little bubble of protection. I can't deal with the y plus 3. It's all the stuff on the outside I need to worry about first. And so I look on the outside for any subtraction, addition there to do, and there's nothing over here being subtracted or added, so I can't, on the outside, so I can't do anything there. And so then division, multiplication. So just like with that 1/2 earlier, we want to deal with the 1/5 by getting rid of the denominator, right? So it's going to multiply both sides by 5. And so, of course, on that side, it cancels the 5. We're left with a 1 on the outside, which, again, I don't need to worry about a 1. If that had been like a 2/5 or a 3/5 or a 4/5, then I would need to worry about that number, but don't need to worry about a 1. So that just gives me y plus 3 squared equals, what's that, negative 35. And we're done with that. So we go to our exponents. Get rid of a square by square rooting. So again, on this side, the square root and the square cancel. So now everything on the outside of the parentheses is gone. So the parentheses can go away. And then on the other side, since we just square rooted, we've got to make sure we do our plus minus. So important to remember that part. And then we get the square root of negative 35. So we're not done solving it, right? Y still has something by it. But I want to look at the right side first and simplify it before I start bringing more stuff over. So, the square root of negative 35 is kind of a complex thing to look at, so I want to simplify that, and then I'll worry about bringing the 3 over. Okay? So I'm going to go ahead and worry about reducing or simplifying that next. And of course, the square root of negative 35 is just equal to the square root of 35 times the square root of negative 1. So we're not going to over-focus on the negative, right, Aiden? We're just going to pull it out. And then we're going to say, hey, 35, you're made up of a 5 and a 7. So kind of like that 6 we saw earlier, there's no buddies, so they don't get to go anywhere. So the only thing we get to do, though, is deal with the I. Right? We can simplify the square root of negative 1 down to I. And the I always goes in front of the radical, not after the radical. So because of what was happening there, because it was not necessarily a prime number, but a number without any square roots in it, or sorry, without any perfect squares in it, the 35 didn't change, right? It just stayed the square root of 35. What we were able to address was the negative, right? We were able to get that to come out as the I. Okay? You guys okay with that? How we went from here to here? So yeah, we weren't done finished, right? We still need to get this 3 over, right? We know how to get rid of a 3. And we're just going to subtract it. And so we just need to be careful about where we put it, okay? Generally with something like this, and we might just put it over at the end or something like that. I'm going to tell you guys, again, just from that kind of convention, to not put stuff after a radical, because if we did put it after, then it might end up looking like this, and then we're just not sure. Again, if you get that kind of leaky radical, you're like, is the 3 under there or not? Okay, I don't want you to do that. So what we do instead is we put it in front. So where this ends up looking, and it's pretty strange looking. Yeah, I don't think you've ever seen a number like this before. That's a pretty complex answer, and in fact, those are called complex numbers. Okay? Complex numbers are made up of a real number and an imaginary number put together. Right? So this is the imaginary part of this number because it's got the I with it. And this is the real part of this number. And the other thing that's kind of weird about this, remember this is actually two answers. One of them is -3 plus I radical 35. The other one is -3 minus I radical 35. So there are two answers. And just kind of understanding what this is, that's role there is, one time we add, the other time we would subtract. Not that we can actually add I squared root of 35 to -3, okay? With what we're doing, well, we understand there is a way to go further with this stuff, but we're not there. Okay? Or will we get there? It's not something that we will do in this class. So, yeah. That's about as gross as it can get for what we're going to do. The stuff that we'll do on Monday will end up looking kind of like this. Some of it will look like this when we're done. Yeah, right, Audrey. Okay. So it's just so foreign, right? It really wasn't a lot of work or anything that was so different for us, like reducing radicals or getting y by itself or whatever. It's just the answer looks so weird. It's hard, kind of like Kyle was saying earlier, like it looks so odd. Sometimes you're like you don't know if you're right, and checking that is actually very difficult. Something definitely we're not ready to, like, oh, well, plug your answer back in and see if it works. That's actually a pretty tricky thing to do with a problem like this. So, whereas the first problem we did today would have been very easy to plug our numbers back in and check them to see if they worked. So definitely not easy, tricky, okay? But I want you guys to give it a shot. I'll stick around and do this next problem so that it's on the end of the video, just in case you guys want to see another one. The other one's actually quite a bit neater, so I wanted to show you the gross one since we were running out of time. And thank you for sticking around, those of you guys that did, so appreciate it. I'll pause the video while you guys leave, and then I'll finish recording it so I can post it. Okay, hope you guys have a good weekend. Let me know if you need anything. Nice seeing you, Sophie. And I really appreciate all you guys that were participating. Makes things a lot more interesting. Let me know if you need help with anything. The only thing I graded, Cam, was the one that you turned in last, or the solving by factoring, and so, but I want you to go back and look at that. I made some notes. I am really expecting more work from that on that. If you kind of go back and look at what this looks like, that's really what I'm kind of more expecting to see in regards to the amount of work that you're showing me, and then most of the students will just do the work on a piece of paper and then send me a picture of it. I don't know if you've done that with any of your classes, like you're taking pictures and submitting them rather than typing stuff out, because it's really hard to type this stuff. So I wrote that in a note to you. So, but I'll have some time this weekend. I'm gonna try to go back and catch up on missing assignments, related assignments. But are you gonna? If we are going to meet this afternoon, or sometime, we can try to figure out what's going on with those stupid online homeworks. Caitlin and Brian, you guys need anything? All right, getting to this last problem. So we still want to use our idea of SADMEP in order to get this by the x by itself. And so looking on the outside of the parentheses for any subtraction addition to get rid of. So of course I see that -20 there, so I want to get rid of that first. So I'm going to add 20 over to the other side. Of course that cancels there. Leaves me with 3 times x minus 2 squared, and that's equal to 75. So that's levels done. I'm going to look for any division multiplication on the outside of the parentheses, so I definitely see that multiplying by 3. So I'm going to divide by 3. And that leaves me with x minus 2 squared equals 25. And then, so we're done with the division multiplication level. So we're going to the exponents level. So of course we have a square here we want to get rid of. So we're going to square root both sides. And again on the left side here, those just cancel, and so we're left with the x minus 2, and there's nothing left on the outside of the parentheses, so the parentheses can go away. And then since we just square rooted, we always want to do our plus minus. And the square root of 25, of course, is just 5. Right? Don't need to make that any more complex than it is. The square root of 25 is 5, but we do have the positive and the negative 5 here. So at this point, because this is a integer, a real number, like it's not like there's no radical, right? And especially there's no I. It's not something like this where I can't take this 3 and actually add it to this and get something different. I can take 2 and add it to 5 and get something different. I can take 2 and subtract 5 from it and get something different. So because this is a normal number, it's not a square root of 5, right? 2 plus the square root of 5 is not something that we can really easily do. 2 times 5i or 2 plus 5i's, again, something I can't really do. So because it's just a normal number, we can actually do a little bit more with this. So it being a normal number actually creates another step, an extra step, compared to if it would a messy number, then we would have just brought the 2 over and be done. So we say x minus 2 equals positive 5, and then we say x minus 2 equals negative 5. So essentially we're just addressing that plus minus and looking at its 2 parts. And so of course I just add 2 over, and 2 plus 5 is 7. And then I add 2 over here, and I get x equals negative 3. So there's our 2 solutions, and we got 2 nice numbers this time, right? It's been a while since we got a nice number. So again, just kind of that idea that if we had graphed that, in order to get one side to be 0, we would have to push that 55 over. So this would be a 75 here, a minus 75 here. So way down on the y-axis, way down there, we have a negative 75, and then have our 7 over here and our negative 3 over here as far as our x-intercepts that we just found. So that graph would end up looking something like this. The vertex would actually be down here somewhere. I just know that from doing these for so long that it's way down there, but it would look something like that. So you can have those problems give you nice answers as well, not just the gross ones all the time. So. All right, hope you guys have a good weekend. Let me know if you need help with something. Take care.